Do you remember a good old oil rig? Oil rig. Maybe that was a mnemonic you used back in general chemistry. Oil rig. Oxidation is loss of what? Of electrons. Something gets oxidized, its oxidation number becomes more positive. Reduction is gain. So in general chemistry, hopefully you might recall calculating oxidation states, balancing electrons even in complicated balancing activities for oxidation reduction reactions. We're not really doing that here, although because you have so much training in that, I will call upon the oxidation state as it is relevant to carbon. Remember, carbon's one of those variable ones, so we look at the more predictable atoms like hydrogen or oxygen that kind of maintain a more predictable oxidation state to calculate the other oxidation states. So if we know, for example, that it's +1 for each H, that's its oxidation state, that carbon here would have to balance it out to be neutral. So that carbon would be a -4. Oxidation state of carbon. And as we oxidize it, and you might look at that and say, how do I know I'm oxidizing it? If you calculate the oxidation state each time, because we know that oxygen contributes a -2, that's different than contributing a +1, right? You're going to change the oxidation number. So as we oxidize it, in organic chemistry terms, we can see how the old school term oxidation came into play. Oxidation in terms of organic compounds really means adding oxygen. Adding bonds to O. You're oxidizing something, and that's true even in non-organic terms. Like you look at, you put iron outside and it gets oxidized. It's making iron oxide, rust, right? So that's kind of what it means. But changing the oxidation number of something isn't a property exclusive to oxygen, which is why you've done that in more broader terms in general chemistry. But as far as organic chemistry is concerned, most of the time when we're talking about oxidation, we're going to be talking about adding bonds to oxygen, usually to carbon. So one bond to oxygen. Oxidize, again, that little bracket over here means an oxidizing agent. Okay, 2 bonds to oxygen. Now look how we have, do this step again, we have 3 bonds to oxygen. Now we have 4, the ultimate oxidized state of carbon. Usually not the goal, but if you over-oxidize or burn something, you'll get CO2, right? And what's the oxidation state of carbon there? We know that oxygen's -2, so this is +4 to make that neutral. So we did increase the oxidation number. We went from -4 all the way up to +4. So the most reduced form of carbon we would say is methane, reduction, reduced number of bonds to oxygen, right? But like we said, other electronegative atoms also play a role here because they have a similar oxidation state. But we represent that reduction process with something that is usually a source of H's. So not just a reduced number of bonds to oxygen or an increased number of bonds to H, while you have less bonds to O. Okay, so usually in order to make bonds to O, you have to remove H's. In order to remove bonds to O, you have to add H's. Okay, so let's get used to these abbreviations. When we write O in a bracket like that, that means we're adding some sort of oxidizing agent. We're going to learn a lot of them. So this is our little generic term for it, oxidizing agent. What always happens to the oxidizing agent? It's a balance. If something got oxidized, that other thing had to get reduced, right? So it got reduced. And that's how you can kind of make sure you're interpreting an overall reaction properly. You watch for something to get reduced if you know that something got oxidized. When we have H in brackets, that does not mean concentration of protons or H ions or anything like that, like you might have used for general chemistry. It means, or molarity, it means reducing agent. It's a source of H's. So our reducing agents are going to be things that you can look at it and see that it has a lot of H's that want to be added to something, often even nucleophilic. So what happens to the H? The H in the brackets, the reducing agent, it's going to get oxidized as it reduces something. If something gets reduced, something else must get oxidized. It always balances out. So it gets oxidized. Okay, so that's our very generic overview of what's going on in oxidation and reduction. So you ready to do the first one? Okay, so you've been oxidizing in the organic sense by adding oxygen to a bond all along, that hydration, right? You increase bonds to oxygen. We're going to do another reaction where we add a bond to oxygen. We're going to make an alcohol from an alkene. You say, wait a minute, we've already made alcohols from alkenes. When we made alcohols from alkenes, what did we get? The OH on the more substituted carbon. And I know what you're all thinking. Is there a way we could ever get that OH on the less substituted carbon? In other words, is there any way we can have an anti-Markovnikov alcohol? You're thinking that, right? The answer is yes. Chemists like that kind of challenge. They would not let that opportunity pass by where there's only one way to add water across the pi bond. So let's think about this alkene here. If we were going to add water across the pi bond, the old way with dilute acid, the OH would go there, more substituted carbon. But this is going to be the anti-Markovnikov way, right? Let's bring him over so for a little more emphasis. So that's our anti-Markovnikov way. So that means the OH, the new OH, is not going to be on there. That's actually going to be the H. And the new bond to the OH is going to be on the less substituted carbon. Look at that. Anti-Markovnikov. Let's see. Here we go. And there. Okay. So let's write that out. Anti-Markovnikov hydration. That tells you what happened. We added an H and OH across a pi bond in the anti-Markovnikov fashion, where the OH went to the less substituted carbon, the H went to the more substituted carbon. The name of this reaction is described as a hydroboration - oxidation. So hydroboration is step one. This is our first two-step sequence that's required to be done to obtain our product we want. They're not considered separate steps that we'd isolate. We need to do them together to get to this end product. So first we use the borane, and that actually adds across the pi bond. That's our source of H. That's our new H here. So one of those H's is going to be that green H. And then later we get the OH down here in actually basic conditions, right? Opposite of what we've done before. So what we're going to do is show the mechanism, and then we're going to try to understand why it works that way. Okay, and some of that will be interspersed. All right, so step one, we're going to involve that borane. So first, let's draw the alkene that we're starting with. Now this first step is the key step. So pay close attention here. Instead of drawing BH3, I'm going to draw out, oops, by the way, I actually started writing something here, but let me fix that. I'm going to draw BH3. I'm also going to write it as BH2 with H to show that for the mechanism, so we can show that bond participating. Just a little note that reminded me over here, BH3 is often written BH3 dot THF. The dot means it's not bonded to it. a solvent that makes a complex with it. That dot means a complex is made. So if you remember what THF is, tetrahydrofuran, THF, that's a common polar aprotic solvent, tetrahydrofuran. Okay, so THF, it stabilizes the borane. Why do we need to stabilize it? It's kind of reactive. It has an open octet, and so it's electron poor, so letting it complex there. It does also tend to dimerize, so you might even see B2H6, it'll still react, but notice the ratio is the same. It's still 1-to-3 ratio, 2-to-6, 1-to-3. So those are, borane comes in various other forms as well. It could have R groups. As long as you have one H there, you can add that H, that green H. So this is going to be our green H. So we need to line that up parallel. This portion right here, let's highlight it. We need to line that up parallel to our pi bond. There's two ways to line it up parallel. We can do this with a pen. B, H, H2 versus BH2, H. Well, knowing that the green H is the one that gets added, it makes sense that it's going to be closer to this carbon because that's the carbon that gets it, right? So this is the right alignment. Don't do that in your mechanism. Why is that wrong? There's two reasons. And they're often the same two reasons for why things happen in chemistry. We just have to know a little bit more than just the answer sterics or electronics. How did the sterics and electronics affect it? So we're going to talk about the sterics first. Well, just look, those ethyls are in the way. BH2 is bigger, right? H is smaller. That's kind of a simple steric argument. BH2 would rather be on the terminal end of an alkene, the less crowded end, right? So BH2 bulkier than H, right? So this is crowded. What about electronics? We always try to look at both factors. Electronics would be, how do the charges distribute or interact? Do we have attractive interactions or repulsive interactions at play? So this is a valid concern because, something to mention here, the electronegativity of boron is actually less. It's about 2.0. So it's actually less than electronegativity of H. We're not used to that. Therefore, we're getting to why that matters. If you have a BH bond, I know that's still relatively nonpolar, but it's not perfectly nonpolar. So if we had to draw sort of a distribution of the charge or look in our Spartan electrostatic potential, we'd see the cooler area would actually be the boron, and the hotter area would be the hydrogen for a change. We're used to that being having a delta plus on it, right? So it actually acts like a hydride. Behaves, instead of like a, we're used to using H's as electrophiles, H+. It behaves as a hydride, not a proton. Hydride means H with its electrons, nucleophile. So it attacks the alkene. So what that means is that in order for it to want to attack the alkene can't be so electron rich. So that means there's going to be two arrows in this step, but we're going to draw them, acknowledge that they might not happen exactly at the same time. So the first proposed arrow is that we know that boron is electron poor. It doesn't have a full octet. The alkene attacks the boron. That means one of these two carbons gets the boron. We've already worked out it's going to be the top carbon because the bottom carbon is a little bulkier in this case. And but there's another reason. If the top carbon gets the boron, this one gets a temporary carbocation. All right, so of the two, which would be a better carbocation? The more substituted. Therefore, when the H is ready to attack as a hydride, that means its electrons are going with it. So you take the arrow and you originate at the bond that we intentionally drew in between B and H, and you attack that carbon. So I'm even going to write in these this difference in electronegativity with a slight dipole here. So delta minus, delta plus. So that would help us understand why the alkene likes to attack the boron first, and then the hydride subsequently attacks that temporary delta plus, right? So unfortunately, I don't get to write a delta plus. I don't get to write a carbocation to explain all that because that is considered a concerted mechanism. However, how I described it was that it was not perfectly concerted. So it's actually considered concerted but asynchronous. And this is really the key step here. So I'm going to write out concerted, kind of like SN2, but asynchronous. What does that mean? Not at the same time. Concerted means at the same time. Asynchronous means not at the same time. It's an oxymoron, right? Well, it's believed to be concerted because you can't isolate or observe that this would last for long. You can't actually attack this boron without this bond breaking and attacking back. But it happens subsequently so quickly that they're wrapped up in the same step. So we can demonstrate this with music. Don't worry, it's not really music, but if I take my drum, or my son's drum, and we say two arrows happen at the same time in a mechanism. Let this be one step, let this be the other step. And it's perfectly concerted, like SN2. Nucleophile attacks, leaving group leaves. That's concerted. SN1, on the other hand, is stepwise, or E1, right? Some of those other mechanisms we've done where it's one at a time. It would be like that, and then you'd wait till the next measure. Then the next step would happen. So there's discrete steps. Concerted but asynchronous is more like, instead of playing them together, you play one right after the other in the same measure. That would be concerted but asynchronous, right? So this would be the alkene attacking the boron. This would be the H attacking the carbon. So in that little break between them, we get like a pseudo carbocation going on. Which is the basis of our electronic argument as to why that alignment is the only alignment that works for the set of reagents. Unboxing this key step, it explains practically everything about, oops, not the wrong one. It explains everything about the reaction in terms of regio and even stereo selectivity, which we haven't gotten to yet. But let's write this out. Okay, so we get here BH2 and H. Okay. Now notice this is now an R group on a, this is still called a borane group, BH2R rather. So I'll call this RH2. In other words, this boron has two more H's that it can attack a starting alkene with. So it actually doesn't need to go grab a new BH3. This will actually keep reacting until all of the H's are gone on boron, all the hydrides. So I'm going to say repeat 2 times until every single, so here's our B, every single H has been replaced with the R group in question. And whatever your R group was, we get to a BR3. That is the end of step 1. Okay. So what that means is you don't need to go, the next alkene that wants to be hydrated doesn't need to go find a new BH3. It actually can react with this. So that's money saving because we can need less BH3. So stoichiometrically, you might even see this written out, especially if you're going to do it in the lab. It's important to know that you only need 1/3 of an equivalent because 3 H's, all 3 of them react with one starting material. So I'm going to write that up here. 1/3 equivalent. Okay, and why? It gets explained here. Hence, 1/3 equivalent. Right? Okay, so that's why the stoichiometry happens. Step 2. We are not done. This looks nothing like our, this started to kind of resemble it, right? This is our green H. And by the way, all of these got the green H right here. H, H, H. So that's our green H. But we need an OH where the B is. So that is the point of step 2. So step 2. Hydrogen peroxide is present, right? It reacts with the hydroxide, and see how those are mixed together above the arrow? OH minus slash, sometimes it's NaOH, KOH slash H2O2. So what is the point of that hydroxide source? It's going to deprotonate the peroxide, and we will use this for the rest of our mechanism, conjugate base. And then that makes water, right, from the hydroxide, plus water. Okay, so that's ready to react with our Br3. I'm just going to write that out as Br3 because now the R's aren't really going to do too much for this step. It's electron rich, it's going to attack that borane. That's, boron, by the way, just so you can get the terminology right. When it makes a bunch of single bonds like to other carbons, like in alkyl groups, it gets the ane suffix, kind of like an alkane. So we get a borane, or if it's just a BH3, just like we'd have a methane, we have a borane, okay? Okay, so let's draw out. We're making 4 bonds to boron. That does fill its octet, but that is boron, remember, is an exception to the octet rule. It has 0 formal charge when it only makes 3 bonds, but that doesn't stop it from being electron poor, right? So let's acknowledge that we just gained a formal charge there of minus. Now, this does an alkyl shift, also sometimes called a migration. In order to get that R group, one of them, their first OH. So lasso one of those bonds, it can go here, and the OO bond, we're going to see we use peroxides actually frequently, and that heteroatom bond we've learned is actually notoriously weak. Like XX bonds are weak, OO bonds are also weak, easy to break. Okay, so what did that do? That released hydroxide. We get a boron back. But now it has an oxygen, BOR. Plus hydroxide. We repeat this until both of these, so this same step, we add some more of this to this. We repeat that 2 more times. Until we get all R groups replaced with OR. This is called, when we have all valencies, free valencies of boron occupied by OR groups, it's called a trialkoxyborane. Why do we name these intermediates? They're like milestones. That's how we know we're getting to the right spot in the mechanism. We're ready for the final step. We're going to release the OR using hydroxide. Attack. And I think we're really answering this question here. You'll see the function very clearly in this mechanism. OR, 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 and OH. Once again, negative formal charge. Some books will have those steps happen at the same time, attack, and that leaves. But finally, this left, we end up with our RO minus, which can be protonated to ROH. Right? We have some water available that will allow it to be the alcohol finally. And of course, this is an acid-base reaction, so we can draw that as an equilibrium. Finally, our alcohol that we made. So, step 1, work out the regio and stereoselectivity. Step 2, clean it up. So the function of this OH minus H2O2 is it replaces the B with the OH, right? That's really what's going on in step 2. So look at step 2, we have our R group, but it has a B on it. You can even think of it like back at this step. We need an OH there to really get to our final product. And so not having it there, we clean it up in this step. That being said, this is kind of a unique, specialized looking mechanism. I like to include mechanisms when they are well understood and presented in the book because they help us track and understand it. But when they are not a parallel trend, I don't actually usually require those be memorized because that's not really the point. So use this part to help you work it out. Know this one though. You cannot understand where things are going unless you understand this part. So that is the key step. That's why it's boxed. So let's write that out. Key step. So in other words, the rest of it, you want to kind of get the main idea, but step by step, I don't usually test on recalling that, you'll see. But this one, you wouldn't really be able to go far without understanding what happened there. Okay. Why? Well, if we say, well, what was the regioselectivity? Regioselectivity was anti-Markovnikov. That can be memorized, but that won't last long. That's short term. Why? If you understood how this lined up, if you really get to the conceptually what's going on here, you'd say, oh yeah, the H had to go to the more substituted spot because of crowding and because of that would be the better carbocation, and it's the H is acting as a nucleophile. So regiochemistry is Markovnikov selective. Excuse me, anti-Markovnikov. Anti-Markovnikov. Stereoselectivity. This one we didn't see an issue because it was not prochiral. What if it was prochiral? We should see there is actually stereoselectivity because this is concerted. Yes, asynchronous, but still concerted, still one step. The B and the H add parallel to the pi bond at the same time. That means they're on the same face. That means wherever the OH ends up, the H is going to be syn to it. So we will do an example with a prochiral one before long, don't worry. Syn. selective. Okay. Digest that one because we have another hydration. Yep, we're going to learn 3 ways to hydrate an alkene. We've learned the second one. See you when you return going through over this. Actually, I'm going to ask you, for example, one BH3 THF, 2 NaOH, H2O2. Give me the answer there. Now this is prochiral. I gave you the information that it's syn. It's anti-Markovnikov. Make sure you have something syn, OH with H, and you have anti-Markovnikov. So that's the stereo. And the regio is anti-Markovnikov. Okay, so let's see what you get when you get back, and we'll move on to the next one.